Okay, so the main thing that I want to do with alkynes is to do as little work as possible. And so we're just going to kind of compare these reactions to the reactions with alkenes. And alkynes in many cases are really similar. So for instance, if you wanted to make an alkene from an alkyl halide, you could do that with a strong base. And so to make an alkyne, you can do that with the addition of 2 aliquots of strong base and do 2 eliminations, one after the other. So that's what's shown here. You could have a geminal dihalide, or you could have a vicinal dihalide where their bromines are on adjacent carbons. And in both cases, you just need a strong base in order to make this reaction happen. So one of the things to realize here is that you know how to make this molecule by doing halogenation of a double bond. And so indeed, if you're doing synthesis of a double bond to make a triple bond, you'd actually first do halogenation in order to make this compound, and then you would use your strong base in order to do the 2 eliminations to give the alkyne. This hydrogen at the end is in blue because that's important. We're going to come back to that at the end of this little PowerPoint. So if we look and compare addition to alkynes compared to addition to alkenes, you can see in many cases you might be able to predict what was going to happen. If, for instance, you do hydrohalogenation for an alkene, you get 1 hydrogen and 1 halogen on your compounds. If you do hydrohalogenation with an alkyne, then you need 2 aliquots of HX, and you will get 2 of your halogens on and that will be that's a geminal dihalide there. So both of the halogens are on the carbon. And then skipping down to halogenation down here, if you do halogenation of your alkene, you get your dihalide. You can then do halogenation twice with the alkyne, and then you get 4 halogens on your carbons there. So the one that's really different is hydration. So let's look at that. Just note that what happens here, kind of the big picture, is that you do get an alcohol next to an alkene if you do a hydration with an alkyne. But then you get this rearrangement happening. It's like a little reaction. It's called keto-enol tautomerism. And you wind up with a carbonyl instead of an alcohol and an alkene. So let's look at how that happens. The hydration of alkynes, the first part of the mechanism, is analogous to what you've already seen with alkenes. So we protonate the pi bond and we get the carbocation intermediate. It is vinylic. It's actually on the double bond, which is a little weird. That's not particularly stable, but there it is. We then get a bond formed to the oxygen of the nucleophile, which is water. And so now we have our positively charged species here. It's deprotonated to give us, this is called an enol. And so it's an alcohol adjacent to a double bond, or actually directly bonded to a double bond. Okay, so that's what we call an enol. And this then reacts whenever you have an enol where you have this OH where the oxygen is actually bonded to the carbon of the double bond. This will then react. It almost always happens. There's a couple cases where it doesn't, but it's almost always more stable for this to rearrange to give us a ketone or an aldehyde. And so one way that can happen is in acid, which is what we have here. And since we have acidic conditions, the reaction just continues in acid. If you had basic conditions, you would also get tautomerization, but this is in acidic conditions, so the reaction just kind of continues until we get that ketone in the end. So, so it's kind of the first thing that happens is an addition reaction. So note that it's the same type of addition reaction we've seen before, where the nucleophilic pi bond reaches out and grabs that proton, leaving us with a positive charge. And so there's now a resonance structure that you can draw with the carbonyl, and then that's deprotonated. And so there's actually not a lot that happens in this reaction in order to get the ketone from the enol. And notice that those are just isomers. So you can also do this, right? You'll also see tautomerization with hydroboration and oxidation, where when you do the hydroboration followed by oxidation with the alkyne, you get an enol, but if you're using a terminal alkyne, in other words, an alkyne at the end of the molecule, then you'll get a terminal enol. And when this does its isomerization reaction, the tautomerization, then you'll end up with an aldehyde as a final product. So hydroboration of the terminal alkyne gives the aldehyde. Can be very handy. All of these reactions in here really help us with our synthesis. I kind of say that as an aside here as we go on, because the next, I'm just going to kind of throw a couple more reactions at you for you to put on your index cards, and we'll end up using them in synthesis. So let's look at reduction. This is the hydrogenation reactions like you saw with the alkenes. With alkynes, you can actually reduce all the way down to an alkane or just to an alkene. Depends what reagent you use, and stereochemistry is dependent on the reagent as well. So if you start with a hexyne, you can use the hydrogenation reaction that we looked at before with a solid surface, that palladium carbon catalyst surface. And what happens is you wind up with like basically just your alkyne touches down on that catalyst. It grabs two hydrogens. You get the cis alkene, but that continues to react, and it gets another set of hydrogens, and then you have your alkane. So that's one thing that you can do, and that's how you get an alkane all the way from an alkyne. A second thing you can do is use a Lindlar catalyst, and so sometimes this is called a poison catalyst, and it's a palladium carbon catalyst again with a hydrogen on it, but this time it also has another little it has like a ligand on it that prevents your alkyne from reacting twice. The alkyne will go down to the catalyst, it will pick up the two hydrogens, but because the Lindlar is there, it kind of stops the reaction at that point, and the reaction's done. You wind up with a cis alkene. And then the third type of reduction is to get the trans. So you can get an alkane, you can get a cis alkene or a trans alkene when you reduce an alkyne. And in order to do this one, you actually don't use that carbon catalyst, because the carbon catalyst is a surface, so that's always going to give you something that's cis. So if you want something that's trans, you actually need something that's just going to kind of give you the electrons. And we use the sodium in liquid ammonia, and what that does is it actually kind of just donates electrons and protons combined to the alkyne, and it makes the most stable product possible, which is that trans alkene. So those are the options for reduction. It's pretty flexible. You can get kind of whatever you want there, and that can be really useful in synthesis. The last thing, we've got oxidative cleavage. For oxidative, there's two more things then. So oxidative cleavage, we saw that with the alkene. With the alkyne, we end up getting carboxylic acids instead of aldehydes and ketones. Just point that out. That again can be useful. But really the main thing that we're going to carry forward with the alkyne, and that we'll use quite a lot, is the formation of the alkynide ion, which is an excellent nucleophile. It's also a good base, so you can't use this with any sort of acidic proton. But what happens is if you add a strong base to your alkyne, you will deprotonate it, and this then is a good nucleophile as well as a base, and you can do like SN2 reactions. And the thing that's really exciting about this is, like, here's an example down here. Notice that what we've done is we've actually created a new carbon bond right here. We could actually then reduce this, right, and get an alkene or an alkane, but we've lengthened our carbon chain, and this is the first time we've seen how to do that. And that's an incredibly important thing in synthesis.